Hi, everyone. Welcome again to the first technical session. This is about serverless computing. So very nice that we had Ricardo set up the stage for this session and actually for this whole conference. This session, we are going to have 4 wonderful talks. I will introduce the speakers shortly, and then I'll share my screen for the speakers to present their lightning talks. That would be the time for the speakers to turn on your cameras. Okay, and just hint me when it is time for me to go to your next slide, and I'll do that for you. All right, so the first paper is about a system called Wukong, which is a scalable and locality enhanced framework for serverless parallel computing. This talk is going to be presented by Ben Carver, who is a master's student at George Mason University, majoring in computer science. His research interests include cloud and serverless computing, machine learning, data analytics, and file systems. Okay, Wukong, Ben, whenever you're ready.
Yeah, I'm ready to go now.
Feel free to have your video on if you would like, and I'll share my screen.
Okay.
All right.
Okay. All right. So, hi everybody. I'm going to quickly highlight the key points of our serverless parallel execution framework, Wukong. So, serverless computing is an emerging cloud computing model with several important benefits and challenges. In terms of its benefits, serverless computing is cost-effective, offering a pay-per-use pricing model in which users are only billed for the resources that they use. The platform also offers high elasticity, as the platform can scale out to hundreds or thousands of concurrently running executors. And finally, serverless computing is automatically provisioned and managed by the cloud provider, thereby relieving users of this notoriously tedious and sometimes time-consuming task. So next, there are these 3 key challenges with serverless computing. The first is that serverless functions often have limited CPU and main memory, and this can restrict performance, of course. Second, there is significant overhead sometimes with invoking additional functions, meaning that it can be difficult to rapidly scale out to thousands of concurrently running functions. And finally, serverless functions have significant network limitations in that there is some outbound only network connectivity. And this can result in excessive data movement and costly communications through intermediate storage, which can further degrade performance. So from these benefits and challenges, we can identify 3 key goals for a serverless parallel execution framework. The first is that such a framework should definitely leverage serverless computing's automatic provisioning and high elasticity to accelerate task scheduling. Secondly, such a framework should take steps to reduce the need for data movement and avoid any costly network I/O when possible, as this has a massive impact on performance. And lastly, a serverless parallel execution framework should offer great cost effectiveness by taking advantage of the platform's pay-per-use pricing model. So this is where our framework Wukong comes in. Wukong is a serverless-oriented, locality-aware parallel computing framework, and Wukong partitions the work of a centralized scheduler across many serverless executors. In doing so, Wukong reduces resource contention while providing automatic resource elasticity and cost effectiveness. And at this point, you could go to the second slide, please. Thank you. So here, I'll quickly identify how Wukong solves the aforementioned challenges of serverless computing. So first, Wukong uses a scheduling technique we call decentralized scheduling to reduce data movement and significantly improve scalability. This includes the partitioning of the input DAG into various subgraphs that are assigned to individual serverless executors. And in doing so, the executors become responsible for only executing the portions of the DAG contained within their assigned subgraph. These executors also perform techniques we call task clustering and delayed I/O to further eliminate data movement and network I/O. And lastly, Wukong leverages this large dynamic pool of serverless workers to execute jobs. And in doing so, it combines the power of numerous individual functions at once to sort of overcome the modest technical specs of each individual Lambda function. So finally, we have these 3 important takeaways. The first is that Wukong's scheduling techniques and optimizations increase data locality reduce network I/O and improve cost effectiveness. And it can enable up to 92.96 tenant-side cost savings. Second, Wukong provides excellent performance and reduces network I/O by multiple orders of magnitude, executing jobs up to 68 times faster than comparable existing frameworks. And lastly, Wukong is easy to use and provides competitive performance against comparably priced serverless frameworks. So that covers my lightning talk. Thank you for listening. So I guess I can see the questions here in the Q&A at least.
Okay, I actually have some questions from VOA also. Let me start with those. Actually,
Sure.
give me 1 second. I will ask, I'll get you started with, one of my questions until I go and gather those.
Sure.
First of all, great work. Thank you, Ben. I'm curious about the initial step of Wukong, where, from a given analytics program, you say you form a DAG. My question is, how hard or easy was this task? I mean, what are some of the challenges, or was it in the context of your work, was it assumed that the application driver basically specifies how to distribute or how to break down a job into smaller tasks and how they are connected to form this data flow?
Right. Yeah, that's a good question. So what we did is we actually used this existing Python framework called Dask. Dask is a framework which automatically parallelizes Python code in a serverful setting, and we reused the programming model from Dask, meaning programs that users have written for this Dask framework can be automatically used on Wukong. We use Dask's DAG generator to generate our input DAGs. That's part of why, or that's the main reason why we compare against Dask in our paper. So we didn't have to design the DAG generation ourselves. There are some challenges with that, though. In our case, specifically with the DAG generation, is that the DAGs that we use aren't necessarily generated for like a serverless context, right? They come from this Dask framework, and Dask was designed to be run in a serverful environment. So the DAGs aren't necessarily optimized for serverless purposes. That's something that, as future work or as a future research opportunity, we could explore. But,
yeah. That would be nice to see. Okay, so I see that you have been active answering the questions, but just for the sake of everybody listening right now, I would like to give you the same question again from Boa. This is from Muhammad Bilal. He asks, as the work is being distributed among Lambda functions, do you run into stragglers? This is a question of interest to me also.
Right. So in terms of how the work gets partitioned to executors, like whether or not it's evenly partitioned, there isn't necessarily a guarantee that in any given subgraph, the amount of work will be the same as other subgraphs. But the way that we partition the DAG, work that can be done in parallel will be contained within different subgraphs. And these different subgraphs get assigned to different executors, right? So because parallel work that can be done in parallel is in different subgraphs, it'll get assigned to different executors and will be completed asynchronously. It'll be completed concurrently. If an executor gets assigned more work than other executors, generally speaking, this work is something that'll need to be done synchronously anyway. Like the tasks will be dependent on each other, one after another, perhaps. And this actually works out because it allows that executor to accumulate all of the intermediate data locally, and it won't have to start going to the network to fetch intermediate data. Whereas if the tasks got spread out more and had these interdependencies, then there'd be increased network I/O, which ultimately leads to worse performance. So the short answer is not really, because if there is a disproportionate amount of work, it's probably a good thing that it gets done locally to avoid network I/O.
Okay, interesting. There is one more question on VOA.
Sure.
I'm trying my best to pronounce the name. I apologize if I get it wrong. Chianki Chu asks, can you talk more about your storage cluster in Wukong framework? Do you consider improving this part in the future?
Yeah, that's also a good question. So initially for our storage, we just used a single instance of Redis. But we found that in particular, as the problem sizes increased, this single instance of Redis wasn't able to keep up, right? It became a bit of a bottleneck. So what we did is we used AWS Fargate which is a quote unquote serverless, a serverless compute engine offered by Amazon. It sort of manages containers for you. And we use a cluster of Fargate containers, each running an instance of Redis. And this allows us to partition the intermediate data and the final results of the workload across this entire cluster. So each individual, Redis instance manages only part of the workload's overall storage needs, and as a result, the storage is a lot more scalable. It can handle much larger problem sizes. We basically spread everything out. That's definitely something that could be improved in the future, though. Just given how big of a difference the network I/O speeds make, that's always something that would deserve more attention, especially with serverless computing and the fact that each individual function is not addressable.
Mm-hmm.
Improving storage is key.
Yeah. Okay. Since we have some more time, I'll go ahead with you have more questions there. So the next question is from Ingo Mueller. Do you see Pyren type of applications which have a tight coupling of several simultaneous invocations as a use case that cloud providers will support, for example, by offering addressability?
Right. So Pyren or Wukong type applications don't necessarily require addressability to be supported by the cloud provider. In particular, when each function doesn't, the state of that function is not used in the future, just given the functions are ephemeral and they're reclaimed, right? So they are somewhat supported now, but that being said, these parallel processing applications will definitely be an interesting target service to be widely supported. And I think IBM Cloud has already started supporting Pyren as a service or supporting it more directly. So I think over time, cloud providers are definitely going to start giving more and more attention to the parallel processing apps in some capacity.
Okay. Last question for you for now is from Rodrigo Fonseca. He's asking, how much work was it to properly provision and size the Redis cluster? Is that serverful part of Wukong challenging? What would you require of the platform to be fully serverless?
Yeah, that's actually a really good question, because we've definitely been exploring the prospect of going fully serverless. In terms of provisioning the Fargate cluster, for me, I hadn't used Fargate before, so I wasn't exactly sure what sort of performance it would offer. So at the beginning, it was more just a lot of guess and checking with basically scaling the Fargate cluster within the bounds of what AWS offers. It wasn't a lot of work in terms of the actual technical aspect of sizing the cluster, and Wukong, as it exists now, sort of handles all of that for the user. It manages the Fargate cluster. The user can configure it specifically if they want to, but Wukong sort of just handles it. In terms of being able to go completely serverless, that's sort of where this outbound only network connectivity thing comes into play, in that it's one of the main reasons it's hard to go completely serverless, because as of right now, functions have to go through some external medium. One thing you could do to be fully serverless as far as the user is concerned is use like fully managed services like S3 for storage. The user wouldn't have to do anything in that case. But in order to get rid of servers completely, you'd have to have a way to communicate between Lambda functions directly. And that's something that isn't currently supported. I know the serverless community is working on like peer-to-peer solutions for Lambda functions, but that's something that would be more in the future, I guess.
Okay, let's thank the speaker. Ben, thank you once again. And that's actually a nice segue to our next talk, which is Particle, Ephemeral Endpoints for Serverless Networking. So that was a good question to stop at. The name of the next presenter is Shelby Thomas. So Shelby, if you are, I see you here, so feel free to unmute yourself and be on video. Okay, there you have. Hi. Shelby graduated this summer from UC San Diego. His research covers distributed systems to data analytics. He has been working on his venture-backed startup since January, decentralizing financial markets. There you go. Let me share my screen and get you set up for your lightning talk. Right. Okay. Let me know when it's time to go for the next slide.
Okay. Yeah, so hi everyone, thanks for being here. So the paper that we presented or will be presenting is Particle, Terminal Endpoints for Serverless Networking done at UC San Diego. So one of the key takeaways for this paper is the first figure that we have, which is that for jobs that require serverless networking, like jobs such as Pyren and Sprocket and Xcamera, network startup really dominates the runtime. So in the picture here, we see the breakdown for using different ways to do serverless networking, such as using overlay networks like Weave overlay, which is extremely popular, Linux overlay, and Docker Swarm overlay. And the takeaway here is that container startup does take a long time, but network startup takes significantly longer, while the application runtime is just a fraction of this. So if we go to the next slide, we can see the approach that we take to solve this problem. So the approach that we take is, 3 steps: observe, identify, overcome. So in the observe, what we did is, we kind of tried to figure out what exactly is going on when we create this sort of overlay network between different containers. There's essentially 3 major phases: create, move, and actually turn on the devices. We identified that this virtual Ethernet movement between different container namespaces ends up being a significant bottleneck, taking up almost 90% of the total time. And after we kind of identified that this was the issue and it's not very performant for the kind of bursty environments that we were targeting, we were able to come up with and overcome this with a tailored solution that's able to reduce the runtime when integrated into different sorts of overlay networks like Linux, Docker, and what you'll see in the paper as well as the poster session is additional benchmarks on these types of burst parallel data analytics workloads such as Sprocket, where we do like a facial recognition using this sort of serverless networking approach. Thanks.
All right. Okay. Let me again have my chance to ask you a question first by the time I read other questions. So if I understand correctly, does it mean that a host will now run function invocations from the same application or the same user? So there won't be a need for isolation. That was your key insight, right, from the talk that I was listening yesterday. If it is so, if that is correct, could there be an impact on utilization of the underlying host? Does that stand in the way of reducing cost, which mainly comes from statistical multiplexing?
So, could you repeat the question one more time? I think, yeah.
Yeah. So if I
Thanks.
understand your key insight, it looked like you're basically suggesting that on one host, you will actually be running function invocations from the same application or invocations that come from the same user, right? And you're saying because it is from the same user, there is no need for isolation. That I understood was your key insight. Correct me if I'm wrong.
Right.
And the effect of that might be that now you're not able to multiplex
Okay.
underutilized resources. So does that happen? And what does that mean for cost?
Right. Yeah. So, and I think in our paper, when we refer to host, the host doesn't necessarily have to be like a bare metal, but it can just be like the VM that it's running on. And so the idea is that like when you're running jobs such as Sprocket and Pyren, basically you're invoking like hundreds or thousands of functions belonging to one user. And so because of that, you don't need that isolation as you correctly identified. And so the question that you're talking about, utilization, I think is like a broader one for these sort of burst parallel data analytics workloads, is that now when you are invoking, 1,000 of these simultaneously for one job, obviously you'll have to maybe do this in a more like rack scale kind of way. You may not be able to oversubscribe on like one host, like this many invocations. Yeah, so it's not a question that we kind of broach in this paper, but it's definitely like a broader question as we see like a lot of papers like, Wukong, for example, like going towards this like massively parallel services. Yeah.
Okay. There's one question that I had noted, and I'll go collect other questions. This was from Kostis Cafes. He's asking, could you elaborate on why it takes 50 milliseconds for, I'm sorry, I might have noted it at a wrong place. Give me 1 second.
Sure.
Sorry about that. No, okay, that's the right question. That is for you. Could you elaborate on why it takes 50 milliseconds for each virtual Ethernet movement? Is there any fundamentally expensive operation?
Yeah, so I think we talk about in the paper this function, this like dev change net namespace, and so by itself, this function is going to be like holding a semaphore while it's doing a lot of notification and waiting. So we know like in a bursty environment, this isn't good. Now to answer the question exactly, like what's going on in that function, essentially there's like a lot of notification and waiting. And so when you are doing this VETH movement, the first thing that it has to do is like a chain of protocols and interfaces has to be notified, and ones that aren't required have to be flushed. So this first happens when the move first starts, and notification happens again when the move is complete. Finally, at the end of the namespace switch, the device waits again in order to get a signal that the moved interface is ready in order to prevent user space races. And so it's essentially a lot of notification and waiting. And then at the very end, it's like successfully moved. So there is also like some variance in this as well, because the other thing that it has to do is also has to wait for all the packets that are currently being received to be done as well.
Okay, thank you. Another question is from Ingo Mueller. How similar you think are the software tracks you use in your study to the ones deployed by the cloud providers? Do the challenges exist there as well?
So right now, cloud providers don't exactly provide any kind of serverless networking, the kind that we're proposing. The approach of taking the overlay is the approach when during our kind of like studies seem to be like the easiest approach in order to do container networking, and it's what people use today for container networking. And given that most of these serverless providers use containers today, we decided to go with this approach. But I don't think that any serverless provider today has serverless networking. That's why we're proposing what are the problems with doing this approach and solutions to actually mitigating it so you don't have this network cold start.
Okay. What do you think are the next steps then? Do you think this can be made into a reality? What are the challenges there?
Yeah, so I think like one of the challenges will be to actually have a use case for it and like a framework built around it. Because a lot of the current frameworks, like the ones I had mentioned before, all rely on using S3 or some intermediate storage as this sort of communication layer. And so what would be interesting would be to see, to actually like build a framework ground up, saying like, okay, let's assume that, okay, now we have serverless networking and we have all of these threads and all these functions available. Like, how do we actually do this sort of communication without using S3 and without doing, going to storage? And that's something that we have a paper in submission working on this sort of framework, like a completely serverless burst parallel framework without having to go to any sort of storage. So just direct function communication. And it builds on top of the particle framework that we have.
Okay, nice to hear that. Thank you. That was all the questions I had. Thank you so much for the lightning talk.
Thanks.
We can transition to the next talk, but I do not see the speaker. So, Tianvi, are you there? Oh, you are now there. Okay.
I just promoted him to panelist.
Yes. Okay. Okay. So the next paper in this session is about characterizing serverless platforms with Serverless Bench, a benchmark that we all need to make progress. The name of the speaker is Tianvi Yu, who is a master's student from Institute of Parallel and Distributed Systems, IPADS, of Shanghai Jiaotong University. She focuses her research on serverless computing during her master's study. Today, she's bringing us a serverless framework that serverless benchmark work that characterizes serverless platforms and gives serverless implications. Let me get you set up with your lightning talk, Tianvi.
Hi.
Hi. Feel free to be on video if you'd like.
It's okay.
Okay. Okay, there you go. 1 second.
Okay, thank you. So here in our serverless bench work, we target the challenging serverless computing that a benchmark suit to reflect the characteristics of serverless computing is still missing. So currently, the application developers who want to build performant and cost-efficient applications have only limited references to make the best of serverless computing. And for the serverless platform designers who expect their platforms to be efficient, scalable, and user-friendly, also needs a benchmark suit to reflect the bottlenecks and the metrics that the users emphasize. So to work towards the problem, we designed this serverless bench, which is a benchmark suit that is designed around the serverless-specific metrics. So specifically in our paper, we first analyzed the 4 unique metrics in serverless computing, which are communication overhead, the startup latency, stateless overhead, and resource efficiency. And this benchmark suite is designed around these metrics. So it includes both micro benchmarks and real world serverless applications and constructs using a variety of composition methods and triggering types. And we conduct 12 test cases using serverless bench and give implications from the evaluation results that we conduct on the open source commercial and private cloud service platforms. And we hope that these implications might guide the future serverless designs. And we have already made serverless bench open source, so we welcome future discussion and contribution to this project. Thank you. Okay, so here is the detail of our test case that's listed here.
All right. Thank you. Maybe. Let me see what questions I have for you. I'll again start with one of mine. First of all, thank you for building this benchmark suite. It definitely is an enabler, right? So I want to thank you from the behalf of all the community. My question, or rather what I was wondering about this is, in building a benchmark, a key question is ensuring that it is representative and not overfitting to any particular aspect of the system or the application. How does serverless bench manage being that representative?
Yeah, so thank you. We emphasize the serverless special metrics in our benchmark suite. We think, and we first analyze the 4 metrics that we think is very important in service computing. And then we include both the micro benchmarks and real world applications. And we select the real world applications based on the popularity as well as the diversity. And for example, in our real world applications, we have the image processing application, which can be assumed as a classic chain application, which is already referenced or evaluated on many serverless computing papers. And for the Alexa Scales application, it's among the most starred application on the AWS Service repository. And we also include an online compiling application, which we think might be a promising use case in the future for service computing. And we also construct the benchmark suite using a variety of computation methods, including the sequence function chain, as well as the nested function chain. And we also use multiple function triggers, such as the HTTP trigger, as well as some user CLI trigger. So we hope these popularity and diversity, as well as the emphasis on the some special metrics, can illustrate our representativeness of this benchmark suite.
Yeah, thank you. There is a question from Alec who's asking, who is using this benchmark? Probably this is too soon to answer, but people are already interested. Who is using this benchmark, and was there any feedback that you received? I think in some sense, this question also asks what I wanted to ask. What are some of the next steps?
Yes, so Actually, we are the first team that use this benchmark. This benchmark has been used by us for about a year, and as we have recently open sourced it, and we are currently setting up the community, and yes, we already received some feedbacks about the future, like will we add some more metrics, and we are also considering more metrics such as throughput or the service billing, which we haven't included yet, and we are still analyze the necessity. And there are also other developers wondering whether we will add some characteristics or metrics from other serverless work, such as the serverless in the wild. And we are still working on them, and we are still developing with the community.
Okay. Probably folks are still thinking of questions, so I'll ask you another one of mine. I think another important point about thinking about benchmarks and building, I think this is a really hard thing to do. So I have many questions like this. How hard or easy it is to use becomes a very important factor, right, in making or breaking a benchmark. I think I remember last year at SoCC 2019, the YCSB paper received the Test of Time award. And one of the key insights that I understood from their talk was that the key thing that they did was they made it really easy to use and to extend, right? And that's what made the suite flourish over time. I haven't seen your paper in detail, apologies for that, but since I have you here, could you maybe elaborate a bit more on the ease of use aspect of serverless bench compared to existing benchmark suites, particularly? Like what makes serverless bench more attractive in terms of ease of use?
If developers are interested, you can go to our website and check the GitHub repo, and we have made I should say that pretty straightforward README or instructions on how you can deploy and run the test cases, and we've already tested them on a variety of serverless platforms. So I think it's also very adaptive to different kinds of service platforms. And yeah, and I highly encourage people who are interested to just try it on. We really welcome contributors to this project, or any issues or questions or hopes that we can work towards. Just give us some feedbacks and issues on this GitHub repo.
Okay, I'll keep that in mind. We have one question from Rodrigo Fonseca. He says, I know it's early, but can you point out some interesting or surprising findings by using the benchmark, either for a particular platform or comparing platforms?
Yeah, actually, many thanks to this question. And actually in our paper, we have 12 test cases, and each of these test case is followed by a serverless implication that we find very interesting. For example, we might find that the proper scenarios or cases where you might want to split your application into multiple serverless functions so that you can get more cost efficient, or save more money, or get your application be more performant. For example, if your application have some parallelizable parts, you can decouple them and split these parallelizable parts into different service functions and run it using the function level parallelization, and you can get better performance of your service application as a whole. And for example, if your application have different execution phases, where each execution phase might need a different level of resource, then you might want to split the execution phases into different serverless functions and allocate just appropriate resource to each of these serverless functions so that you can save your cost because the billing is actually proportional to your provision resource. And by splitting the application in this way, you can save costs while maintaining the performance. And we also have other suggestions on the application side as well as the platform side. And so I think it's interesting to find out these implications in our paper. And if you're interested, I can explain more about other implications on this paper.
I think we have another question. So at this point, I'm going to ask Rodrigo to take this offline. The other question is, again, I'm trying my best to pronounce your name, is by Stergios Anastasidis. I completely messed that up. Sorry. The question is, did you have the chance to experiment with network storage access, and what is your experience with that?
Okay, so in our evaluations for network storage access, we mostly interact with S3 because it's the default communication intermediate or the default network storage for AWS Lambda service platform. And my experience is that it's very slow, obviously, and everyone knows that. And if you notice that in our paper, there is a communication evaluation, and we evaluate the communication payload from a small payload to a larger payload. And we are evaluating on OpenWhisk FN as well as AWS Lambda. And for AWS Lambda, we use the AWS step function to construct this function chain. And this AWS step function has a limit of the maximum payload that you can directly pass across in the functions. And if this payload is larger than the 32 kilobyte, you have to go through S3 to do this communication. And we can obviously see a significant latency jump by communication through S3 than direct communication using step function between the two functions. So I think S3 is still a slow network storage. And I already saw some serverless papers starting from, I think, in 2018 to do some work to optimize this network storage performance. And I also saw some paper in this SoCC conference. And I would be very willing to see more optimization on this field because it's very needed in this community, I think, because you have to use these network storage, and if it's bad performance, then it's very hard to construct these high performance complex applications, which are composed of several serverless functions, which have to be interacting and communicating with each other.
All right. I think that was the last question that I had. So thank you so much, GNV.
Okay, thank you.
And we'll move on to the last presentation in this session, which is about photons, lambdas on a diet. And the presenter's name is Vojislav Jukic. I hope that was close enough. I practiced.
That was very close.
Great. He is a fifth-year PhD student at Systems Group at ETH Zurich, supervised by Ankit Singla. His research interests lie at the intersection of computer systems, networking, and cloud computing. So after your lightning talk is done, I'll introduce your co-author also. Okay. And you have like almost 20 minutes, so feel free to answer at length.
Oh, that's great.
Okay, I'll get you.
Can you just bring up slides?
Yes, 1 second. There you go.
Hello, everyone from Zurich. I'm Wojciech Jukic, fifth-year PhD student. I'd just like to quickly highlight the main features of our system called Photons that tries to improve the performance of serverless computing by lowering the overall cluster memory utilization and decreasing the number of cold start events that functions observe over time. So actually, the main insight is relatively simple. If we look at the execution of one particular function, one particular function invocations, let's say in this case, function F1, we observe that each function has to spawn a bit of isolation layer like OS or container, then runtime, libraries, shareable state, and a bit of local memory for invocation-specific computation. Now, if we have two executions of the same function, we have to do the same. We need a separate stack for each of these functions. For 100 invocations, we need 100 separate stacks. This causes two kind of overhead that we have to tackle, we want to tackle with our system. First, we consume much more memory than needed because each invocation requires only a bit of memory for memory-specific computation, while the rest could be shared. And second, spawning each stack takes time, which is what Ricardo explained at the beginning as a cold start. So to minimize both of these overheads, we designed Photons, a system that provides the same abstraction as today's serverless platforms, but allows allows invocations of the same function to be collocated within the same container. So each function has a bit of local state and everything else is shared within a container. Can we just go to the next slide? Yes, thank you. Looking at the concrete workload, this is the image classification workload you see on the left, and we break down the memory consumption into multiple components. We see that the shareable components that comprise runtime, libraries, and shareable state, because this is a machine learning workload, this is actually a machine learning model, consume up to 90% of overall memory consumption. So that means that if we collocate multiple invocations within the same runtime, we can save 90% of memory. This is in ideal case if we have all the functions running concurrently at the same time and all invocations are of the same function. Now, if we look at the cluster behavior and the real workload published by Microsoft recently, and Ricardo discussed that workload, we observed that if we use today's platforms, the utilization of a cluster oscillates around 70%. Memory utilization oscillates about 70%, while if you use Photon, the memory utilization is reduced by 30%, which is quite a substantial memory saving, but it's not that interesting per se. What is really cool about the saving is that we can keep more warm containers in memory. And on a Microsoft workload, we observed that this additional memory and keeping more warm containers can reduce the number of cold starts by 52%. So just to summarize in one sentence, we collocate multiple invocations of the same function within the runtime, provide the same abstraction level as today's platform, reduce memory consumption by 30%, and reduce the number of cold start events by 52%. And with that, I'm done with my lightning talk, and I'm happy to answer your questions.
Thank you, Voislav. Okay, so we have Rodrigo Bruno joining. Yes, okay, thank you. He's also on video. So Rodrigo is a co-author on this paper, and he's a senior researcher at Oracle Labs, Zurich. His research is mostly focused on combining systems and programming languages to optimize cloud applications. So welcome both of you again. I'll start with an obvious question, I think, that has been lingering in my mind. Running multiple invocations in the same runtime, what are the security implications? Wouldn't this mean that one user will be able to observe other users' invocations that may leak patterns, which is a lot of information if you think about it. So how does Photon address that? Any security privacy concerns for that matter?
I think that's a great question, and this is like obvious thing we have to deal with in some way. And there are multiple layers at which we could address the issue. So first of all, we run only invocations of the same function, which implies the same user, but very same function within the same container, which minimizes this, let's say, problem to some extent. However, this is still not enough for all the functions. And then what we propose is actually that users have to mark their functions to be photon friendly. So if the function processes very sensitive data and cannot afford to have this kind of, I'm not sure if I should say security, potential security issue, it should be run as a normal serverless function with a strong memory boundary and strong isolation instead of being run within the same container. However, I would argue that many functions can afford this kind of this environment in which they're co-executed with other invocations of the same function, because this is something that happens on today's platforms to some extent. For example, if you look at Microsoft or Azure, the way warm containers work, they're actually polluted by previous invocations in many situations. This is marketed as a feature rather than a security issue. But if you had a malicious, so if you have an execution, if you have an invocation that does something sensitive, and the next invocation that's collocated within the same container is malicious, you have to some extent, a security problem. And I think users are willing to pay this price for getting better performance, and with photons reduce number of cold starts and overall memory utilization.
I see. Okay. I know this was a difficult question, so thank you for that answer. There is a question from Preeti Murthy. She's asking, since Photon does not reduce CPU utilization, the number of containers that can be packed on a host is CPU bound. Wouldn't that mean doesn't that mean memory going underutilized and wasted on the hosts?
I think that's a great question, and it's a really important observation that we don't save CPU cycles. So we are only talking about memory utilization and reducing the consumption there. However, this this free memory can be reused to host more warm containers, which translates to less cold starts, or in some sense, less CPU cycles wasted to spawning a container and spawning the runtime and so on. So we still use this memory, we just use it for a different purpose, which is hosting warm containers.
Okay, there are many questions, so I'll keep going. The next one is by Mohammad Bilal. In your experiments, do you observe significant variance in memory increment needed based on function inputs?
I think it's a really important question to be answered, especially if we're talking about deploying photons on a production level cloud platform, because users ultimately have to figure out what we call memory increment, or the size of a private state, because with photons, the first invocation occupies the entire container exactly as today's platforms. But for the second collocated invocation, you just increase memory allocated by a tiny bit, which is actually a private state. So you have to figure out how to compute this private state. And in the paper, we actually try to give some insights and details on how to do that. That said, I think there are functions that definitely have this problem where private state can vary substantially depending on the input parameters. However, this is, I believe, a problem that must be tackled even with today's serverless functions, because we have to decide on the maximum memory that will be allocated to our function. So yes, but there are ways to tackle this problem of variability in the private state.
Mm-hmm. There's another question, which I think is similar in vein to the question I asked. This is from Marius Kogias. Can you make some comments on the isolation guarantees? What happens if a function invocation leaves behind state? Is this a bug or feature?
I think it's a great question. So what we do right now, we have our implementation is in Java JVM. So there we provide memory isolation first between collocated functions at the runtime layer. And then after the invocation finishes, we clean up the state of that particular invocation. However, because it's sometimes very useful, and it is marketed as a feature on today's platforms, we enable invocations to leave state for future invocations. So there is a shared object store that can be used by invocations to explicitly leave state for future invocations. So yes, we do have a cleanup phase, but we also allow sharing for future invocations.
And by the way, I'm not calling you out, Rodrigo, but feel free to interrupt if I'm going too fast and not letting you speak. Please feel free.
No, that's good.
Okay, so jump in. There are
I'll
many
wait
other
for you.
questions.
I'll take the questions if you want.
Okay. So there's a question on the Zoom Q&A. This is from Gohar Irfan. He's asking, is this similar to what Azure Functions does by having multiple invocations handled by the same runtime instance until some threshold is reached, at which point more instances of the runtime are spawned?
I think it's a great question, and it is similar to a large extent. However, Azure Functions provide a slightly different abstraction model compared to AWS, and we're targeting the abstraction layer where each function still assumes that it's running in a complete isolation. So in a spirit, yes, but in a implementation, in the concrete details, it's substantially different.
Mm-hmm. I will take another question, which is from the same person, Gohar Irfan. For applications in languages like Python, where multi-threading is not super efficient, are multiple invocations spawned off to a different process than the initial runtime or worker, or as separate threads?
So could you repeat the question?
Yes.
I'm sorry.
No problem. For applications in languages like Python, where multi-threading is not super efficient, are multiple invocations spawned off to different processes than the initial runtime or as separate threads?
So this current work, so can I take this question, please?
Yeah.
All right. So the current work is for Java, for JVM. So it supports Java or any language that builds to bytecode that runs on JVM. The whole point of doing this thing using photons is to avoid using sub-processes. Because if we start doing that, eventually we will start polluting memory and pulling more memory pages into our sub-process, and thus defeating the purpose of using photons, which is to share the most amount of memory and to go into very fine granularity for sharing. So if we would do photons for Python, I would manage using threads or some kind of abstraction that uses threads, even if you have to have a better way to implement threads in Python, or some kind of task abstraction in Python that will be efficient enough.
Mm-hmm. Thank you. There's one more question from Alec. It is not only memory, but also number of concurrent threads supported in one function. How does it compare to setting concurrency target in Knative serving?
So there is, I'm not sure about Knative, but there is a similar option, I think, in OpenWhisk, which allows you to have concurrent functions in some particular runtimes that allow it. For example, I'm thinking of JavaScript. So JavaScript and V8 allow you to have multiple invocations of some JavaScript code in different isolates. However, this has the problem that these isolates are isolated in memory, and hence the name. So they do not share any state, and this prevents us from sharing libraries and sharing, for example, machine learning models. This also has the disadvantage that all these isolates will have their own code cache, meaning that you will always going to pay the price of profiling and cheat compiling the code over and over again. And this is why we wanted to build something new, that we could share the code cache, we could protect the code from multiple accesses to the same state, but we could still provide an abstraction that would allow the user to share in a safe way large chunks of data.
Okay, last question. This is from Prateek Sharma. Can you compare the memory savings versus page sharing, such as KSM?
So I guess we did an experiment to try to measure this. So we tried to do sub-processing. So using this idea of the zygote process, there's a couple of papers, recent papers that use this idea as well. And the idea is to launch a function, warm it up, and then whenever you receive another invocation of the same function, you just fork the current process and you do this invocation and you take advantage of all the memory that is already pre-warmed up, the runtime is already ready, and so on. You can save some memory, but we noted that the benefits by using photons allows us to save so much more memory, because eventually runtimes start polluting memory by running GC or by having things that move inside the runtime that are completely oblivious to the function, but still pollute memory and bring more pages into the subprocess. I'm not sure if Vojislav wanted to add some details to the answer or not.
I think you covered it all. We have experiments that tackle exactly this case, and we show that this copy and write mechanism ultimately produces additional memory overhead that can be substantial for very small workloads.
All right, that was my last question. Thank you so much. And we are finishing in a good time. Thank you so much. Christina, handing it over to you.